let us discuss one of the most important areas of chemistry, that is P block. You know, in the periodic table we have 4 blocks, S, P, D and F, and S, D and F block elements, all S, D and F block elements are metals. They are all metals, all S, D and F. But this P block is a very mixed bag. It contains metals, non-metals, even half metals. All these are present in P block only essentially. So, as per the definition, what is the definition of P block? If the differentiating electron, what is differentiating electron? The last electron, differentiating electron, last electron enters P sublevel, then it's called P block. So, you can have the electronic configuration ranging from NP1 to NP6. Therefore, there is scope for 6 groups in P block. That is 3A, the elements of 3A, which start with boron, aluminium, etc. Elements of 3A. And elements of 4A, carbon, silicon, etc. Carbon, silicon, germanium, stannum. In fact, you need to memorize the elements. It's very important. The group number. In fact, the Roman numbering is more important than anything else. Elements of 5A, the nitrogen family, nitrogen, phosphorus, etc. 6A, oxygen, sulfur. 7A, fluorine, chlorine, bromine, iodine. And the 0 group, where we don't have much to study, helium, neon, argon, krypton, xenon, radon. They are noble gases and their chemistry is not of any interest, though some of them form compounds, especially xenon. Xenon forms compounds, and the compounds of xenon are not very much useful. So, there is not much excitement in 0 group, and all others, they are simply gases, inert gases. So, you can say, and this 3rd group also, only boron is a non-metal, all others are aluminium, etc. They are all metals. So, you can say this group is also not much of interest. You only have boron as a non-metal. All metals, their behavior is almost similar, like they are reducing agents, they lose electrons, they are electropositive. Therefore, there are no variations, in fact, compounds of metals and metallic properties. But in non-metals, there are so many variations. You will come across compounds and you have to know their properties. You should know their hybridization, shape. So many variations are there only in P block. S block, D block, F block, you can in fact collectively study. You can study them as a chapter called metals. Though there are some individual differences when it comes to their ability to react, but they all have almost same unique properties, right? And you know, carbon is a very important element. We have a different branch of chemistry in the name of carbon itself, organic chemistry. So, the new numbers that have been given by the IUPAC are 13, 14, 15, 16, 17 and 18. And of course, 13, 3, 14, 4, 15, 5 means just add 10 to get the new number. 3A means 13th group elements of. So, let us take a particular group, any one of the groups as an example. Say for instance, elements of group 15. Elements of group 15. 5A. Nitrogen family. Nitrogen family. They are also called nicogens. Nicogens. What does the name suggest? Their compounds cause suffocation. Their compounds means compounds of the elements of a fifth group. Their compounds cause suffocation. So, this alternate name or a pseudo name perhaps is not very much necessary. If you know it, it's okay. Otherwise, you need not be particular about such names. The elements of group 16, they are called chalcogens, meaning ore forming nature. Elements of group 7, they are called halogens. So, there are so many variations like that. Their compounds cause suffocation. Which of those compounds cause suffocation? What are the elements? Nitrogen, phosphorus, arsenic, antimony. They are slightly toxic also, poisonous in nature. Arsenic compounds, or arsenic itself is a poison. Arsenic compounds, even phosphine is also poisonous, pH 3. So, you know, nitrous oxide, N2O, which is called the laughing gas, is used as the modern day anesthetic, used in surgeries as an anesthetic. So, their compounds of group 5, they cause suffocation, therefore they are called nicogens. I repeat, you need not be interested in such names. Nicogens, chalcogens, halogens, right. So, what is that we should study about a particular group? Any group for that matter, you should know the elements, obviously. Nitrogen, the symbol N, nitrogen. Phosphorus, P. Arsenic, antimony, Sb. You know, it's called stibium in Latin. Stibium. Bismuth. So, from the names itself, first instruction is learn some of the names taken from other languages other than English, like you have cuprum, ferrum, because while naming a compound, especially in the coordination compounds, we use the Latin name only. For example, AgCN2 minus, it is a complex of silver. It is called dicyanoargentate 1. Argentate, the Latin name of silver, is used there. So, I am not highlighting anything here, but I am only reminding you that you should be aware of Latin names also. So, the fact that antimony is called stibium should remind you that means from any group, you can take any group and you should know what to learn from that group and what are the similar things in other groups. Learn Latin names. Cuprum, ferrum, argentum, aurum, natrium, kalium, stannum for tin, plumbum for lead. Like this, you have 10 or 11 names from Latin and wolfram from German. Wolfram, we have antimony here, ferrum, cuprum, wolfram, that is from that is for tungsten and from German. So, learn Latin names so that you can use them in naming complexes. So, elements of group 16, you should be aware of the same. Oxygen, sulfur, selenium, tellurium, polonium. Just parallel to this group 6. Oxygen, sulfur, selenium, tellurium, polonium. So, from any group, you should know the names, their symbols thoroughly, and their atomic numbers. Nitrogen is 7. The atomic number of nitrogen is 7. How can you find the others from starting with this 7? 7 plus 8, 15, plus 18, 33, plus 18 again, 51, 83. What is the rule governing this? It's okay, I have added 8 here, 18 here, but how? What is the general rule? You just look at this. Between 2 and 12, both including between 2 and 12, add 8. 2 and 12. Suppose 7 lies between 2 and 12, add 8 to get the next one. The rule only up to less than or equal to 12. Less than or equal to 12. And then 12 to 39, including 39, add 18. Greater than 39, add 32. There ends the matter. So, 15 lies between 12 and 39. Therefore, I have added 18, 33. 33 once again lies between 12 and 39, 51. 51 is greater than 39. 39, add 32 to get 83. So, using this rule, you can go about atomic numbers of all elements in perhaps all the groups. Apply this again for copper, silver, gold. They belong to the same group. Copper 29. How about silver? 29 plus 18, 47. 47 plus 32, 79. So, just remembering 12 and 39, less than or equal to 12, less than or equal to 39, and greater than 39. You divide the numbers into three limits. Less than or equal to 12, less than or equal to 39, and greater than 39. Then, physical state of all elements. You should know the physical state. You know nitrogen is a gas. Nitrogen is a gas at room temperature. Phosphorus is a solid, and so do all others in this group. So it's okay if you know about a particular, just one group, but what about all elements? You have 115 elements. How can we go about the physical state of all elements? So you need to have a procedure for all things like that. For everything like that, you adopt a procedure and stick to that procedure. Now, physical state. So, if I give you a particular list, physical state of all elements, very few are gases. Very few are gases. Who are the gases? Helium, neon, argon, krypton, xenon, radon. The noble gases of the zero group, the end of the periodic table, and the last group of P block. These are gases. Fluorine, chlorine again are gases. Oxygen is a gas. Nitrogen is a gas. Hydrogen is a gas. That's all. Only these are gases. A handful of them. You hardly have maybe 5 plus 6, 11. 11 gases at room temperature, of course. Physical states are measured at room temperature only. Now, very few are liquids. Bromine and mercury. Only two, I consider only these two as liquids. Of course, gallium, cesium, francium, there is a doubt on their being liquids. Strictly speaking, they are solids at room temperature, like they have melting points around 27, 28, 29. So let's not waste any time on those three. You stick to bromine and mercury are clear-cut liquids. These are clear-cut gases. Actually there is no doubt the melting point suggests room temperature is 25. They should be solids only. But let's not waste any more time on that. Gallium, cesium, francium, put a question mark and leave them. Just forget them. Liquids. And all others are solids. All others are solids. Here you are. So, after learning just 13 elements, you come to know about 115 elements. This is a smart way of learning things. You put more in that all others category. Classify many in that category. Just highlight or just learn these few only: gases, liquids, and all others. That's very easy, gases, liquids. So now you can give the physical state of all elements. Physical state of all elements. The entire P block, you can easily give the physical states. Now, and you can even say all S, D, and F block elements are solids except this mercury. All S, D, and F block elements. All S, D, and F block elements being metals, they are solids. Only mercury is not a solid there. And as I told you, cesium, francium, there is some element of discussion on that. Let's not worry about that. So, all these gases are present in the P block only, except of course hydrogen, which is written separately in the periodic table. Hydrogen has its own place. You can say H block, a block for itself. The S block, and this is the D block, and this of course is the P block, including helium. Elements of group 15. Physical state. Then nature of all elements. Nature. Especially metallic, non-metallic nature. Very few are non-metals. Very few are non-metals. Helium, neon, argon, krypton, xenon, radon. All these are non-metals. Fluorine, chlorine, bromine, iodine, oxygen, sulfur, nitrogen, phosphorus, carbon, silicon, boron, and hydrogen. Only these are non-metals. Only these are non-metals. And we have a few half metals, metalloids in our syllabus. Half metals. Germanium, arsenic, antimony, selenium, tellurium. It's enough if we know about these five. Of course, there is some discussion once again whether astatine is a metalloid or not, astatine, polonium, even bismuth. But let's confine to what our discussion is implied. You need not be particular about everything. Broadly, it is enough if you know these are half metals. One or two additions and subtractions can always be there. Let's not be very particular about that. Instead of trying to find out everything and not knowing anything, let's at least have a broader idea. What a half metal, what is a half metal, semi-metal, or a metalloid. Metalloid. That way at least what happens is you will have some language of chemistry to speak. If somebody asks you what do you know about sulfur, you should be able to say it's a solid, it's a non-metal. At least 3-4 basic things about all elements. We should not look like illiterates when it comes to the language of chemistry. After learning chemistry, you should be able to speak a few words, if you say a few things about at least all elements. Now, half metal, metalloids, and all others of course are metals. All others are metals. And I once again tell you, there are in the lower classes, boron is given as a half metal, the lower classes, the NCERT textbooks and all. Why it's there like that? There is no clear cut boundary line separating a metal and a non-metal. You don't have a yardstick. You can't say if the electronegativity is so much, it's a metal, it's not. There's no clear cut yardstick. But then why did I classify boron and silicon here? The IIT JEE syllabus itself classifies them as non-metals. Preparation, isolation, properties of the following non-metals, the very first chapter of inorganic chemistry, starts with boron and silicon. So the JEE syllabus itself classified them as non-metals, and no harm if we also treat them like that. Right. I'm only giving you a broader idea. I'm not telling you anything pinpointedly about each and everything. Nature of all elements. Then atomicity. It's once again important. Atomicity of all elements. Atomicity. Very few are diatomic. Very few are diatomic, like F2, Cl2, Br2, I2. O2, N2, H2. Only these are diatomic. These are diatomic. There is just one element that is triatomic. Triatomic. Ozone. Atomicity of all elements, and of course ozone is also an element. Oxygen, the dioxygen O2 and O3 are two allotropic forms of the same element called oxygen. Oxygen is the name of the element, and its allotropes, or oxygen is the name of the element whose symbol is O, and its allotropic forms dioxygen, the usual oxygen. We call it oxygen, and that is correct also. You need not particularly say dioxygen. And the trioxygen, which is called ozone. So these two are only allotropic forms of the same element once again. Oxygen is the element, O2 and O3 are its allotropes, different forms of the same element. So ozone again is an element, triatomic. Then very few are tetraatomic. P4, AS4, SB4. Octatomic. S8, Se8, Te8. Octoatomic. All others are monoatomic. All others are monoatomic. Mono. Once again, there is some ambiguity regarding gallium, whether it is diatomic or not, and that's not there in our scope. And like this, there are so many debatable things in chemistry. One author may treat gallium as diatomic, another one may treat as. So it's important to know our limitations. We cannot waste all our time discussing whether it is monoatomic or diatomic. If it is mentioned in a reasonably, authentic textbook like the NCERT or somebody, maybe we have to use that knowledge. We cannot go about discussing things which are controversial. I won't say controversial, but debatable, depending on perception. So, atomicity of all elements. Now, having said that, you should be able to do the same work for everything. What is that we have discussed so far about nitrogen, phosphorus, etc. The name, the symbol, the atomic number, how to find other atomic numbers for all other groups, oxygen, sulfur, selenium, tellurium. Then nitrogen's physical state, that it is a gas, that it is a non-metal, and that it is diatomic. So if you make a tabular form sort of thing, this is diatomic. you should be able to reproduce the same for all elements. Oxygen's atomic number 8, that again is a gas, that is a non-metal, that is also diatomic. Oxygen, of course, it has two forms, O2 and O3, diatomic as well as triatomic. So you should be able to imitate the same for all groups. It's the distribution of electrons in the main levels. Nitrogen 2, 5, since the atomic number is 7, 2, 5. Phosphorus 2, 8, 5. Arsenic 2, 5. In what way does this help us? All these elements have 5 electrons in their outermost shell, which once again reminds us or justifies their position in the group 5A. Elements of group 5A has been the heading. So 5, they have 5 electrons. Therefore, this old group numbering, the Roman way of, the Roman numbering is at least will remind you of the valence electrons. Elements of 7th group, they have 7 electrons. 5th group, 3 short of the octet, 3 short of their octet. So group 5A. Nitrogen, phosphorus, etc. Distribution of electrons in the main levels. Arsenic, antimony, bismuth. What about general electronic configuration? General electronic configuration. For the A subgroups, A, 1A, 2A, in the old numbering we have A and B, 1A, 2A, 3A, etc. Divide the electrons between NS and NP. For example, 5A, 2 plus 3. Divide the electrons between NS, 2, NP, 3. That way, that 2 plus 3, 5 will once again remind you this is the electronic configuration of a 5th group element, group 5A element. 5A. 7A. Distribute this 7 between NS and NP. NS2, NP5. NS2, NP5. 7A. 4A, NS2, NP2. Like that. General electronic configuration. Then B subgroups. It is N-1D and NS. Distribute the electrons between N-1D and NS. Like for instance 7B. Put 2 electrons there in S and the rest remaining here. N-1D5 NS2. 4B. N-1D2 NS2, like that. 2 plus 5, 7B, 2 plus 2, 4B. If you are using S and P electrons, it is the A subgroup. If you are using S and D electrons to add, that is the B subgroups. They belong to the D block. So, by just looking at the electronic configuration of an element, you 3D3, 4s2. Whose electronic configuration is this 3D3, 4s2? Okay, it must be 5B, someone from the D block. 5B, 3D3, 3D1, 3D2, 3D3, scandium, titanium, vanadium. 3B, 3B, 4B, 5B, etc. This is scandium, titanium, vanadium. So 3D1, 3D2, 3D3. So it reminds you of so many things. 3D3, 4s2. You know 3D comes only after 4s. After 4s, 3D comes, therefore it's the 4th period. The element belongs to 4th period, 4s2, 4th period. And of course D block. And 5B. How do I know it's 5B? Add this 2 plus 3, 5. 5B. So 4th period. So from the electronic configuration, you should be knowing so many things. And of course you should know this the layout of the periodic table, the layout, broader layout, start 1s, 2s followed by 2p, 3s followed by 3p. So in the second and third periods you don't have the D elements because 3D comes only after 4s, 4p. But after 4s it is 3D. So if you just look at the way electrons enter, you also know the structure, broader structure layout of the periodic table. 4s, 3D, 4p. 5s, 4D, 5p. 6s, 5D, 6p. 7s, 6D, 7p. After 4s only the 3D starts, after 6s it is 4f, 5f. So, the moment you see 4s, you have to say it is a fourth period. 2s2, 2p3, second period. The valence electronic, the outermost configuration, suppose somebody has 4s2, 4p4, you can immediately point that to the fourth period, the p block, and the fourth period of p block, and overall 2 plus 4, 6, it's 6a. 6a, oxygen, sulfur, selenium group. Oxygen is 2s2, 2p2, therefore sulfur, selenium. This is the electronic configuration of selenium. If you know the general electronic configuration, you can relate the electronic configuration to the group, to the block, to everything. So be thorough with this, be thorough with this. For example, somebody having 4d2, 5s2. Observe this, 5s, 4d. So this element belongs to the D block. The D block. How do I know? The last electron is in D. 5s is full, 5s2, 4d2. So D block. Fifth period. How do I know this is the fifth period element? Fifth period. Because 4d comes only after 5s. You can see 5s, 4d. Now, if you have a D, you add 1 to get the period number. 4d, it's the next 4d, fifth period. And 2 plus 2, 4b, the designated group, 4b, 2 plus 2. So, fourth group, you have titanium, zirconium, hafnium. Of course, this is zirconium. Titanium, this is the electronic configuration of zirconium. We need to know only the 3D elements, not 4D, but I'm just telling you. But you should be thorough with the 3D elements, scandium, titanium, vanadium, etc. Okay, that we will of course discuss in D block. But as of now, if an electronic configuration is given, you should directly take me to the particular element. 6s2, 6p3. Who could this be? 6s, 6s, 6p. Here it is, 6p. Okay, p block, 2 plus 3, 5a. Oh, the present group. Sixth, 2s2, 2p3. You know this is nitrogen. 2s2, 2p3. Nitrogen, phosphorus, arsenic, antimony, bismuth. This is the electronic configuration of bismuth. So given the element, you should give the electronic configuration and vice versa. And how about atomic number? You already know. 7 plus 8 plus like 15, 33, 51, 83. 6s2, 6p3 is 83. Or better still, you know 6p6 is radon. Radon. The end of sixth period is radon, 86. The end of first period is helium. Helium, neon, argon, krypton, xenon, radon. Whose numbers are 2, 10. Add that principle again. The principle I have taught. Less than or equal to 2, add 8. Add 8 again. 36. 86. So 83, 86 minus 3. 86 minus 3 is 83. Right on. Right. 6p6. 3 short of 6p6, 3 short of radon, 3 short of 86, which is 83. So you should do this with some kind of interest. These addition, subtractions. If you observe the arithmetic in the layout of the periodic table, you will have better understanding of chemistry. 4s2, 4p5. Where should you directly take me to? 4p5. 4p5. 4p6. The end of fourth period is krypton, 36. So this is 35. So helium, neon, argon, krypton. Just one element behind. Fluorine, chlorine, bromine. This is bromine. 4s2, 4p5. 2 plus 5. 7a halogens. 7a halogen. So neon, 9, element number 9 is fluorine. Fluorine, chlorine, bromine. This is precisely bromine. So it's not at all difficult to relate the atomic number, electronic configuration with the element. All these things can be learned only through observation. You observe the variations, the trend, what exactly each element of a particular group. Suppose nitrogen has 2s2, 2p3, nitrogen, phosphorus, arsenic, antimony, bismuth. You just need to imitate 3s2, 3p3, the valence shell configuration, 4s2, 4p3, 5s2, 5p3, 6s2, 6p3. So, we have discussed distribution of electrons in the main levels and electronic configuration also. Right. So, we are not confining ourselves to this heading, group 15, because every time I have been repeating, it's about all elements, physical state of all elements, general electronic configuration of all elements. Once again, elements that exhibit allotropy. Elements that exhibit allotropy. All the elements that exhibit allotropy. In general, metals do not exhibit allotropy. In general. This way, we have avoided a big headache because large majority of the elements are metals and they don't exhibit allotropy. Only a handful of elements exhibit allotropy. And of course, stannum, bismuth and polonium are exceptions to this. They are exceptions. Means though they are metals, they exhibit allotropy. Metals that exhibit allotropy, only a handful of them. Now, elements that exhibit all the elements, let's make a list. Boron from the third group, look here. Boron, carbon, silicon, germanium, stannum, everyone from the, these four from the fourth group. Carbon, silicon, germanium, stannum, everyone except lead. Phosphorus, arsenic, antimony, bismuth. That is, except nitrogen, everyone in the fifth group. Oxygen, sulfur, selenium, tellurium, polonium. All these exhibit allotropy. All the elements from the sixth group. Except nitrogen, everyone from the fifth group, and except lead, everyone from the fourth group. Stannum, bismuth, polonium, they are metals, but still exhibit allotropy. So, if I ask you, what do you know about a particular element? At least you have So many things to talk about that. What do you know about sulfur? If I ask you, what do you know about sulfur? What is it you know about sulfur? Its symbol is S. Sulfur. It's a solid. Of course, it's a powder, amorphous, solid. It's a non-metal. It's octoatomic. Octoatomic. It exhibits allotropy. It belongs to a group called chalcogens because of their ore forming nature. Very interestingly, even the names, the properties, why do you think group 5A they are called nicogens? Nicogens. I already told you, because of their poisonous nature, toxic nature, suffocating their compounds. Not all their compounds, but some of them. Their compounds cause suffocation. Why? Why do you think they cause suffocation? Look at a compound of fourth group, methane, and that of fifth group, NH3. Sixth group, H2O. Carbon, nitrogen, oxygen. I have taken 3 different groups. Fourth group, fifth group, and sixth group. You will now know why I indeed started with this fifth group. Look at methane. It's forming 4 bonds and it doesn't have any unused pair of electrons we call lone pair. So, fourth group, there is no lone pair. But what about group 5? Group 5, after forming 3 bonds, 2 electrons are left. And these 2 electrons, they are called a lone pair. Ammonia, there is a lone pair. A pair of electrons which is not being used. H2O. Sixth group, there are 2 lone pairs. 2 lone pairs. After forming 2 bonds, you know, oxygen belonging to the sixth group will have 6 valence electrons and only 2 of them are used and 4 are unused pairs. Fourth group, no lone pair. Fifth group, 1 lone pair, and sixth group, 2 lone pairs. Look here. Suppose you inhale methane through your respiratory process. Methane is inhaled. What happens? Nothing. It doesn't dissolve in blood. It cannot form any bonds. But ammonia has a smell, pungent smell. It is slightly toxic. Why? It has a lone pair and it can form a bond with some of the ions in the blood. We have so many ions, especially iron 2 in hemoglobin. So, this ammonia can form a bond with the human system. Some of the ions in our body. What about water? You laugh if I say it is toxic or it is poisonous. It in fact saves life. Why? Oxygen has 2 lone pairs and it doesn't want to get rid of a lone pair, in the sense that even after losing 1 lone pair, there still is another lone pair. It's not very enthusiastic to lose that lone pair. But whereas in the case of ammonia, if it forms a bond with the lone pair, the 4th bond, what happens? It immediately goes from pyramidal to tetrahedral. It gets relief in the form of strain in the bonds. Ammonia gets relieved. Water, there are 2 lone pairs. Even if you get rid of one of them, there's not much anxiety in water to lose the lone pairs. Therefore, group 5, especially, they are poisonous. pH 3, once again, there is a lone pair. So, to have poisonous nature, the element, the compound must be able to form a bond with blood, I mean something inside our body. To form a bond, you should have residual valency. The residual valency means unused pair of electrons. So, in fourth group, you don't have that kind of a thing. Sixth group, they are not eager to lose that lone pair. So, fifth group is typical, group 5A is typical. That's why. Now, why are these elements called chalcogens? Chalcogens. Because of their ore forming nature. You imagine a metal on the surface of the earth, above the earth. Who can the metal combine with? In air, what is it you have? You have noble gases, they don't react. You have carbon dioxide is not very highly reactive. Nitrogen is almost inert. Nitrogen is almost inert because of its triple bond. It is highly stable and it doesn't react easily. It takes a lot of voltage for nitrogen to combine with oxygen in air. Only when a lightning occurs, nitrogen combines with oxygen. So, what else is there in air? You only have the highly electronegative oxygen. Therefore, most of the metals combine with oxygen forming oxides, metal compounds. Most of the metal compounds which we call are ores are oxides. Hematite, magnetite, bauxite, Al2O3, Fe2O3, all those elements. Most of them are oxides. I am not saying all of them. So, once again, all the elements of of this group, oxygen, sulfur, they don't form ores. Some of them. All the compounds are not poisonous. Some of them. So, looking at few of them or some of them, their name is given. Chalcogens. And most of the ores are either oxides or sulfides. Why? Above the earth, you have only oxygen in the environment, and under the earth, you have sulfur. The reactive substance is sulfur. So, metals combine with sulfur when they are down below the earth. So, most of the ores are either oxides or sulfides. So, oxygen and sulfur have great affinity towards metals and they form compounds of metals which are called ores essentially. Now, so even the name has a meaning, I don't deny, but at the same time it takes a lot of effort on our part to remember all these pseudo names, alternate names. It's okay if you remember them, but don't consciously try to learn them. In course of time you will be learning them. And halogens, the 7 halogens. Halo means C. Without these elements, fluorine, chlorine, bromine, no C would have been a sea. The sea water is salty. The sea water contains so many salts, chlorides, especially sodium chloride. Suppose these chlorides and fluorides are not dissolved in that sea water, you won't call that sea. The water would be good enough to drink. That once again will become a river. So, they are the compounds of these elements, that is fluorine, chlorine, bromine, iodine, they form salts which are water soluble and they end up in the sea. That's why sea water of course is salty. Now, next, what else you know about ore forming nature? What else you know about sulfur? You know oxygen, sulfur, selenium, oxygen 8, 16, 286, sulfur belongs to 6A of the periodic table. Since you know the electronic configuration of oxygen, 2s2, 2p4, I told you 6, divide the 6 between S and P, 2s2, 2p4, sulfur 3s2, 3p4. The outermost electronic configuration is 3s2, 3p4. So, physical state, atomicity, and you know sulfur exhibits allotropy. But just looking at very few list, a short list I have made. I have made a list of metals and non-metals, physical states, atomicities, allotropies, and I have given a rule for general electronic configuration. Just going through 5-6 lists, you will talk like a literate person rather than saying, what do you know about rhodium? Somebody asks you, what do you know about rhodium? If you haven't heard, even if you haven't heard about it, you must have the, talent rather. You must have the ability to say, okay, though I haven't heard about it, rhodium, it's a metal. Why? We have never seen that in non-metal and half-metal list. It's a metal. It's a solid. Because rhodium belongs to all other categories. And it is monoatomic. Most metals are monoatomic only. So, you have at least 3 sentences to speak out 115 elements rather than saying, never heard of it. What do you know about niobium? I also don't know much about this because we generally don't study deeper into the D block. Niobium. But the name aluminium, calcium, the name suggests, okay, metal. So, it's very easy to remember which are non-metals. All sounds ending in N. All the sounds ending in N. Like helium, sulfur, phosphorus. All sounds ending in N, helium, sulfur, phosphorus are non-metals. Non, like fluorine, chlorine, bromine, iodine, carbon, silicon, argon, radon, krypton, all names are ending in N. Helium, sulfur, phosphorus, these are non-metals. And most of the metals will have calcium, magnesium, So M for metal, N for non-metal. Very interesting. It's a simple observation. You just observe. That's how one has to learn chemistry. You can learn on your own if you apply your mind. You observe the common factors. You remove the common factors. You identify the common factors. You classify. You classify it yourself. Periodic table will help you a great deal. Just have the periodic table in front of you. Look at the names. Look at their respective positions. Look at their electronic configurations. There is gradation in every group. That is the purpose of classification. Otherwise, why would we classify elements? All elements of a particular group should have the same properties. Once again, vanadium, niobium, tantalum. So, niobium, okay, it's a metal, it's a solid, it's monoatomic. Or at least you have 3 or 4 sentences to talk about all the elements. What about oxidation states of all elements? Oxidation states of these: nitrogen, phosphorus, arsenic, antimony, bismuth. The maximum oxidation state is equal to group number. Of course, copper is a chief exception. The group number, the old numbering. The chief exception being copper. Copper is an exception. We discussed this in a different context also, all about oxidation states. Maximum oxidation state is equal to group number and minimum oxidation state. Minimum oxidation state is equal to group number minus 8. This is for 4A to 7A only. For instance, nitrogen. Which group does it belong? Nitrogen belongs to group 5. Group 5, not 15. This 15 is not of much use. 5A. Maximum plus 5. Minimum minus 3. Group number minus 8. 5 minus 8. Same is the case with phosphorus also. And so, apply the same logic for sulfur. Maximum sulfur. Maximum plus 6, minimum minus 2. Sixth group, chlorine. Once again, chlorine plus 7 minus 1. So, using this maximum minimum, you can talk about the oxidation states. What about the oxidation states of this particular group? Though we have learned for all elements, we have to apply whatever. So, minus 3 to plus 5, it has so many oxidation states. Phosphorus also, minus 3 to plus 5. And of course, these have plus 3 plus 5, plus 3 plus 5. And bismuth also has plus 3 plus 5. But bismuth prefers plus 3 for some reason. Bismuth prefers plus 3 to plus 5 due to inert pair effect. Between 3 and 5, bismuth prefers lower oxidation states, and that is called, preferring lower oxidation states is called inert pair effect. Right. Oh, arsenic and antimony being half metals, you can't strictly say they have a negative oxidation state. Very rarely they may have a negative oxidation state. And remember, we should never discuss that occur very rarely, occasionally. At our level, especially our level, the class 12 JEE level, you should know your limitations. You should not talk about occurrences, very rare occurrences and very unusual compounds. Don't take any interest in them, at least in the initial stages. You should not be interested in those sporadic occurrences which occur very rarely. So, plus 3, minus 3 to plus 5. So, you can do the same for sixth group. What I am doing is taking group 5 as an example and applying that to every group. So, the moment group 5 is over, I intend to complete the entire P block. How come? The same. Oxygen. Of course, oxygen is a different case, minus 2 to plus 2. The minimum is minus 2, maximum is plus 2. Very rarely oxygen becomes plus. And the minimum rule, if you have observed, I gave it 4A to 7A only. What will happen to other groups? What about 3? I mean, first group, second group, D block. They are all metals whose minimum oxidation state is 0. Metals can never go lower than 0. For example, manganese, 7th group, 0 to plus 7. 0 to plus 7, it exhibits any oxidation state, but never less than 0. Okay, one or two cases you might have seen by mistake, you might have seen a negative oxidation state of manganese. They are called uncommon oxidation states. I repeat, never take any interest in uncommon things, abnormal things, because we are all normal human beings. Be normal to yourself. Manganese minus 1, vanadium minus 1. Oh, don't take any interest. 0 plus 7. 0 to plus 7. So, all others, metals, titanium. Okay, fourth group, 0 to plus 4. Like chromium, sixth group, 0 to plus 6. Of course, they are all 6B, 4B, 7B. They are all called designated as B.